Hello everyone, I'm Yusuke Hatakenaka. Now I talk about PCB design condition to suppress the oscillatory false triggering of parallel connected GaN-FETs. First of all, GaN-FET has excellent performance, but it has a disadvantage of low threshold voltage and easy to cause false triggering. Especially, the oscillatory false triggering is serious issue that can occur in GaN-FETs. The oscillatory false triggering is a self-sustained oscillation phenomenon induced after fast switching. We observed it in an experimental one-pulse test circuit. In this figure, the red waveform shows the drain voltage, and the green waveform shows the gate voltage. After the turn-off, the gate voltage repeated the turn-on and off without control at about 120 MHz. So, this oscillatory false triggering may cause enormous switching loss and the damage of electric applications. We try to solve this problem by using equivalent circuit transformation and analytical approach. We thought that the cause of oscillatory false triggering was a parasitic oscillation circuit. Lg and Ld is a parasitic inductance of power circuit and gate circuit. The Ls is a parasitic inductance of shared path between the gate circuit and power circuit. And these Cgs, Cds, and Cgd is a parasitic capacitance of GaN-FET. By analyzing the oscillation condition of this circuit, the design instruction to suppress oscillatory false triggering was cleared. I'll review this condition later. This presentation is an extended version of the suppressing method of oscillatory false triggering on the previous page. We focused on the use of GaN-FET in high-power applications. Currently, there are no GaN-FETs with high current rating. Therefore, the parallel connected GaN-FET is attracting attention to use GaN-FETs under the high current conditions. By increasing the current rating, the GaN-FET are expected to be used in high power applications, such as power converter for electric vehicles. The concern is oscillatory false triggering with parallel connected GaN-FET. The fast switching at high current is easy to cause false triggering. In addition, the parasitic oscillation circuit of parallel connected GaN-FET has a complex parasitic element networks, and analysis on previous page cannot be applied. To use GaN-FET in a high power application, it is necessary to propose new design instruction to suppress oscillatory false triggering with parallel connected GaN-FET. Purpose of this study is propose a PCB design instruction to suppress oscillatory false triggering of parallel connected GaN-FETs. First, I review the case of single GaN-FET. Second, I analyze the case of parallel connected GaN-FET. Finally, I will show an experimental result. I review the case of single GaN-FET. I will convert an evolution circuit to parasitic oscillator circuit. First, because the oscillatory false triggering has very high frequency, we can regard capacitance Cin and diode D1 is short circuit. On the other hand, we can regard the inductance L1 is open circuit. As a result, we can get the AC equivalent circuit like this. So, we try to transform this equivalent circuit. The point here is apply the star-delta transformation to the network of parasitic inductance. As a result, we can get a transformed equivalent circuit like this. The oscillation condition of final equivalent circuit is expressed by the following condition. According to this condition, we found the ratio of common source inductance Ls and gate drain capacitance CGD is a key factor for effective prevention. Next, we consider the case of parallel connected GaN-FETs. To simplify the discussion, we focus on the two parallel connected GaN-FET. First, as in the case of single GaN-FET, we perform the equivalent circuit conversion for high frequency. Note here that the parasitic inductance of power circuit is divided into LDA, the common path, and LDB, the switch current path. The converted circuit forms a complex network of parasitic elements, and analysis of this circuit is difficult. Here, to simplify this circuit, we apply the star-delta transformation to the parasitic inductance network of LDA and LDB. As a result, we can get a simplified equivalent circuit like this. We note here that the drain source voltage of parallel switches are in phase and same amplitude. This is because PCBs of parallel connected switches are usually designed symmetrically. There is no potential difference at LD', and it is open circuit. As a result, we can convert into a parasitic oscillation circuit similar to single GaN-FET. From this circuit, we derive a non-occurrence condition of oscillatory force triggering with parallel connected GaN-FET. Also in this case, the ratio of LS and CGD is a key factor for effective prevention. However, the parasitic inductance value of power circuit is different from the case of single GaN-FET. In particular, the area shown in green, we can see that the non-occurrence conditions are smaller in the case of parallel connected GaN-FET. Therefore, the case of parallel connected GaN-FET requires a different design from single GaN-FET. We conducted the two experiments of theory demonstration. First, we compare the experimental results and proposed suppression condition of parallel connected GaN-FETs. Second, we compare the difference in the suppression range between the single GaN-FET and parallel connected GaN-FET. The experiments were conducted in a single pulse test circuit using two parallel GaN-FETs. A capacitor inserted between the gate and drain of the switch, and the ratio of LS and CGD to set each value. And we investigate the occurrence of oscillatory force triggering by one-pulse switching test. First, we show a comparison between the proposed theory and the experimental results. The left-hand side shows the experimental results, LS versus CGD. The red region is the suppression range of oscillatory force triggering, shown proposed theory. Also, theoretical and experimental non-occurrence region were consistent with each other. The right-hand side shows the waveform under two conditions. Under the CGD equal 49 picofarad, VGS and VDS is oscillate in the same phase. Under the CGD equal 12 picofarad, the oscillatory force triggering didn't occur, and result is consistent with theory. Thereby, we could confirm the oscillatory force triggering could suppress by appropriate designing the ratio of LS and CGD. Next, we show a comparison between the single GaN-FET and parallel GaN-FETs. The right-hand side shows the experimental results under the same conditions with the single GaN-FET. So, the experimental result in the green circle show that the oscillatory force triggering is more likely to occur in the parallel connected GaN-FET. Therefore, the PCB design for parallel connected GaN-FET needs to follow the proposed design instruction specialized for parallel connected GaN-FET. Summary and conclusions. The proposed design instruction specialized for parallel connected GaN-FET is better to use GaN-FETs in high-power application. That is all I have to say. Thank you for your attention.